This is 3.9, separating solutions and mixtures. Our outcome is I can leverage intermolecular forces to separate components of solutions. So chromatography separates components of a mixture based on the differing intermolecular forces of the components. We also have this mobile phase and the stationary phase. So based on how those molecules that are being separated interact with those two phases, we can separate them. So if a compound is able to interact strongly with the mobile phase, it will move quickly through the stationary phase. If it interacts with the stationary phase strongly, its progress is going to be slowed. So we can kind of balance these attractive forces in order to separate a solution or mixture. So there's lots of types of chromatography, many types of different stationary and mobile phases for many different purposes. We can also have mixtures of mobile phases, or we can even engineer stationary phases that have very specific properties. You can even do like a 2D separation. So, like if you have paper chromatography, you run chromatography up the paper and then you turn it 90 degrees and run it up the other side, and then that will give us a two-dimensional separation of components. So think of it as just a highly customizable way to meet the exact needs of a separation. So this is useful beyond forensic science, right? You usually do, your paper chromatography separation with spinach leaves or a marker or something like that. But we can use it well beyond those sort of forensic science applications. So, for example, if you have well water, if you live in the Mayo area like I do, you're going to have an ion exchange water softener. And what that is it's just taking advantage of uh, things like iron and calcium and their differing attraction for a resin in order to separate that out from your drinking water. So once a mixture is separated, we can use other analytical equipment to identify it or do other tests. So to prepare a chromatograph with paper chromatography, we're going to draw a straight baseline across the bottom of our filter paper or our chromatography paper. We're going to do that with pencil. And that's because pencil is not going to interact very strongly with your solvent, and it will stay in place. Then we want to place a dot of our mixture. So in the example, it was ink, but you're going to want a very small, very dark, concentrated spot. We're going to put some solvent in a beaker, and then we want to put the paper into the beaker, making sure that that solvent level is below the level of our dot. Then we can put a lid on it to prevent evaporation. We're going to wait, and then we can remove it from our developing chamber once the solvent has reached near the top. And then what you're going to want to do is mark that with a pencil for later measurements. So here we have a separation occurring. We have a mixture of pigments that are being separated using paper chromatography. The surface of the paper is made of cellulose, which is moderately polar. The mobile phase is hexane. So looking at this molecule of hexane, it's going to be nonpolar because it's got a very symmetrical electron distribution. So the only major intermolecular force present is going to be dispersion forces. So which component interacted more strongly with the stationary phase? That's going to be component A. So it interacted with the stationary phase more, which slowed its progress moving up the paper. So which component is more polar? Well, my stationary phase is polar and my mobile phase is nonpolar. So since component A interacted with my polar stationary phase, that would conclude me to believe that A is more polar. What if we switched out the hexane for isopropyl alcohol? So isopropyl alcohol is a little bit more polar. So if we add that as our mobile phase, then our mobile phase is polar. So now it might be that component A moves further up the paper, whereas component B would move more slowly due to its weak interaction with the mobile phase. So how do we quantify how far these travel? We use a retention factor. So this is the distance traveled by the compound divided by the distance traveled by the solvent front. So here's a really nice diagram that shows exactly what's going on when we have a mixture of solvents. So here we have a mixture of isopropanol and water. And isopropanol is a little polar, but not nearly as polar as water. So the water is going to interact really strongly with the surface of the paper, and the isopropanol is not going to quite interact so strongly. So my solvent front is kind of like this 2D solvent front here, where some of the isopropanol is just a little bit ahead of where the water is because it can move a little bit more quickly than the water can through the stationary phase. So using a mixture of the mobile phases allows the chemist to kind of very finely control the polarity and other properties of a solution. So we can refine this to improve the separation for substances with similar intermolecular forces. So this has lots of applications. For example, if someone is a restorative chemist, so somebody who does things like art restorations, they might use solvents to clean a painting, but they want to adjust those solvents so that they don't damage the painting, but they still are effective at cleaning it. So they balance those intermolecular forces by testing several mixtures of solvents. If the mobile phase was adjusted to be more polar by adding more water, how would this impact the separation? So my separation would become poorer because there would be less separation between those molecules. The most polar molecule would travel further, while the least polar won't travel as far. So we would see a difference in how those particles, those molecules get separated. So here we want to provide evidence that this mixture is the same as what we saw in question 3 here. So how can we prove that? Well, we have a very nice ruler here so we can measure and we can calculate the RF values here, and we see that they match or very closely match depending on the error of our measurement. They very closely match the RF values given in the previous diagram. So since both of these were conducted under the same conditions, they result in the same RF values. So you really don't look up like a book of RF values to figure out what something is. You more use this when you think you know what it is and you can compare it in your lab by two chromatography setups run under identical conditions. This is a chart that summarizes the different types of chromatography. So we have paper chromatography, which we've gone over a bit. So those molecules are separated on the basis of how they interact with the stationary and mobile phases. My mobile phase is going to be a solvent, water, alcohol, hexane, whatever. And my stationary phase is going to be cellulose / paper, which is moderately polar. In the case of thin layer chromatography, very similar to paper chromatography, but instead of paper, we have a highly polar thin layer of silica. So my TLC plate is like a little piece of plastic that's covered with this sort of chalky silica layer that's incredibly smooth and flat. And it's a very highly polar surface. In column chromatography, a mixture is added to a column that's packed with the stationary phase and it's soaked with the mobile phase. So we keep adding solvent, which carries the more soluble compounds down the column faster, and then we can catch those in a beaker. So usually the stationary phase is silica or alumina, which is highly polar. But again, we could engineer special resin beads that have very specific properties, kind of like how a chemist might adjust the ratio of solvents that are being used. Another process that we can separate components of a liquid mixture with is distillation. So this takes advantage of the fact that the different liquids will have different boiling points. Boiling point depends on the strength of those intermolecular forces for each component. So the water jacket provides cold water that flows through this glass piece, and it allows the vapor to cool and condense while in the water jacket. A fractionating column basically has a bunch of surfaces where substances with higher boiling points can condense and return back into the liquid. So it increases the concentration of the desired substance in the vapor. So the condensed vapor is made only from one type of molecule. So when you boil a mixture, that vapor is going to have some of all of the components. The fractionating column helps us to remove some of those components so that what we get is more pure. Simple distillation works well to separate a liquid from a solution, such as when water is distilled. We collect the distillate, which is going to be very pure, clean water. Fractional distillation is for separating mixtures of liquids. So we have a mixture of ethyl and butyl acetate, and we're going to separate this using distillation. So these are both liquids. Which compound would initially be present in a high concentration in the distillate? So the molecule with the lower boiling point would be present more in the vapor, as it has weaker intermolecular forces that are holding it together as a liquid. So both molecules are polar and both have dispersion forces, but ethyl acetate is a little less polarizable because of the smaller size of the molecule. So butyl acetate would have a slightly higher boiling point. So it would come out of our distillation after ethyl acetate. So when you conduct one of these distillations, you actually have a thermometer stuck inside your system. And while that thermometer measures a constant temperature, that's how you know that you're getting this compound or that compound, because that will be the temperature it boils at. So how can we use intermolecular forces to influence solubility to separate mixtures? So we can use the relative interaction between a stationary and mobile phase and a molecule to speed or slow that molecule's progression through the stationary phase. And this allows us to